Hello everyone, I am Khushi Jodhani.
And I am Naitreja Sani.
Today we are presenting storing and non-restoring division algorithms in computer organization. In this presentation, we will first understand binary division, then registers that are used. After that, we will study restoring and non-restoring division with its examples and flowcharts, and finally compare them with real-world applications. In this slide, we are going to learn the introduction of binary division. So the binary division is used in computers because CPUs cannot directly divide numbers. They use repeated subtraction methods. This process uses three registers, A, Q and M, and runs for n cycles. At the end, Q stores the quotient and A stores the remainder. A is the accumulator which stores the partial remainder. Q initially contains the dividend and finally gives the quotient. M is the divisor and remains constant throughout the process. So now let's move to the restoring division and its algorithm. Restoring division works on repeated subtraction. If subtraction gives a negative result, we restore the value back. First, we initialize A to 0, Q with dividend and M with divisor. Then we shift A and Q to the left and subtract from M from A. Now we check the sign of A. If A is negative, we set Q0 to 0 and restore A by adding M. If A is positive, we set Q0 to 1 and keep A as it is. This process repeats for n times. Finally, Q gives the quotient and A gives the remainder. In the flowchart, we start with initialization, then perform shift, subtraction and sign check inside a loop. Based on the sign, we either restore or continue and repeat until all bits are processed. Let's understand restoring division with its example. Example of 7 divided by 2. Initially, Q is 0111, M is 0010 and A is 0000. We perform shifting and subtraction step by step. Whenever A becomes negative, we restore it by adding M back. After performing all iterations, we get the final quotient as 0011, which is 3 in decimal, and the remainder is 0001, which is 1 in decimal. This example clearly shows how restoring division works step by step. Now let's understand non-restoring division and its algorithm. Non-restoring division improves restoring division by removing the restore step inside the loop. First, we initialize A, Q and M. Before each operation, we check the sign of A. If A is positive, we shift and subtract M. If A is negative, we shift and add M. Then we set Q0 based on the sign of A. We repeat this for n iterations. At the end, if A is positive, we perform one final correction. In the flowchart, we check the sign bit first, then decide whether to add or subtract and repeated the loop. Finally, we do a correction if needed. Now, let's take the same example of 7 divided by 2. We follow a similar process, but here we decide whether to add or subtract based on the sign of A. Instead of restoring immediately, we adjust in the next step. After all iterations, we get the quotient as 3, and after the final correction, we get the correct remainder. This shows that non-restoring division gives the same result but in a more efficient way. In this slide, we do a side-by-side comparison between restoring division and non-restoring division. Let's start with restoring division. In this method, after every subtraction, we check if the result becomes negative. If it does, we restore the previous value by adding the divisor back. So inside the loop, a restore step is required. Because of this, each iteration may involve two operations, subtraction and sometimes addition. Also, after the loop finishes, no extra correction is needed. In terms of performance, it can up to 2n clock cycles. But the circuit design is simple and easy to understand. That's why it is mainly used for learning purposes rather than in real CPUs. Now, moving to non-restoring division, here we avoid the restore step inside the loop. Instead, we decide the next operation based on whether the result is positive or negative. So each operation performs exactly one operation, either subtraction or addition, but not both. At the end, if the result is negative, we perform one final correction. This method takes exactly n clock cycles, making it faster than restoring division. However, the circuit is slightly more complex and it is a bit harder to understand. This is the flowchart of restoring and non-restoring division algorithm, which was explained in above slides along with the algorithms of both the division algorithms.
Now let's see a logistic circuit implementation. In hardware implementation, both methods use similar components like register, adders, subtractor, and multiplexer. The main difference is in how they are handled and restore operations. Restoring division performs restoration inside the loop, while non-restoring division avoids it and handles correction differently. Both circuits were tested with the same example and produced correct results. This is a logistic and we implemented restoring and non-restoring division algorithm and it is used similar standard digital logic components. From this diagram, here are the main components used. First, register A, Q and M. A is used for accumulator, Q is used for quotient, M is used for division, used to store values during division steps. Second is adder or subtractor. Block label A plus M and A minus M. Perform arithmetic operation required for divisions. Third is multiplexer. Used is clearly visible in the lower section. Select between result of A plus M or result of A minus M based on the sign bit of A. Fourth is shift register, shift register or shift left register. Block label 1 bit left shift used to shift combined A Q register during divisions. Fifth is combinational logic or wiring. Combines A and Q register used during shifting operations. 6. Sign bit detector. Label. Sign bit of a decision bit. Checks whether A is positive or negative. 7. Is constant. Always 1 or 0. Used to set bit in Q depending on the conditions. 8 is splitter or bus line. Green multi-line connectors used to handle multiple bits like 4-bit or 8-bit data. 9. Control logic. Through not clearly labeled, control signal are used for shift enable or multiplexer selection or operation selector like adder or subtractor. So this is a non-restoring circuit. At this part, it is used for 1 bit, so we combine 4 times. It gives us 4 bit non-restoring divisions. This is a restoring circuit. Here we gave inputs in divisor 0, 1, 0, 0. 1. Here we give input divided in 1, 0, 1, 1 or accumulator inputs give 1, 1, 0, 0. Here we simulate enable. So first before shift left operation, this is a shift after shift left operation. So this is a 4 times combined circuit. That's why it gives a 4 bit and 4 bit out. This is a quotient and this is a remainder. So we got quotient 1010 and remainder 1100. This is a 3D circuit. This is a 3D circuit overview. First of all, with dividend it give 7 and divisor give 2. First of all, we load. So whichever we give input, it load first here. Second, step 1, it loads and according to algorithms, it performs the operations. Here we choose auto. So it gives direct us to answer this which is a quotient 3 or remainder 1 or total operation is 10. This is non-restoring division. We first load. So whichever we give input, it first load. Step 1. step 1. First of all, whichever step 1 is performed, like based on algorithm, we give auto, so it directs computes output, and we give direct output. So quotient is 3, remainder 1, and total operation is 8. Now you see, restoring division and non-restoring division, number of operations are different. So restoring division is not better than non-restoring division. So it means non-restoring division is better than restoring division. Here is side by side comparison. We Here we run both. As you see, a remainder is 3, quotient is 3, but here restore step is 3, restore steps is 0. So non-restoring division is better than restoring division.
To summarize, restoring division is simple but slower due to extra operations. Non-restoring division is faster and more efficient because it avoids restoration inside the loop. In real-world applications, non-restoring division is used in modern processors like Intel and AMD. It is also used in embedded systems and FPGA designs for better performances.
Thank you for listening to our presentations. Thank you, guys.